All right, let's talk about z-scores, z, that magical value on your normal distribution curve, okay, your standard deviations from 0. Chapter 6, to find our z-score, given a value, we had x minus the mean over the standard deviation. Now, that was giving us a z-score when we were talking about a population. Okay, so all of the problems from chapter 6 were given in the context of a population. Remember, population is all. Okay, now we're going to be doing in chapter 7 the z-score for a sample, from a sampling distribution. Okay, so when I have just a piece of the population and I'm going to force that to my normal distribution curve. So that is going to be given by, okay, these are our symbolisms here. So you have x bar, which is just the x value in a sample, minus the mean of the sample. Okay, and it's written here twice because this here, the mean of a sample, is equal to the mean of a population. We looked at that previously in 7.1. Okay, and then this is over the standard deviation of the sample. So the part that changes in this calculation is the denominator. Okay, so what the actual calculation is going to be is like this. You have x bar, so the x value in the sample, minus the mean, which is equal for the sample and the population, and then this is changed. So the standard deviation of a sample is going to be given by the standard deviation of the population over the square root of the sample size, which is n. Okay, so the denominator changes in this calculation. So let's take a look at an example for this. So we have a population has a mean of 276 and a standard deviation of 81. Out of that population, I'm taking a sample of 40. So you'll see an extra sentence in the question like this: a sample of this many is drawn. Okay, what is the probability that the mean of the sample will be less than 273? Okay, so let's pull out the information we need to tackle this problem. Okay, we have the sample size is going to be 40, that's your n. Okay, you have mean of the population is equal to the mean of the sample, which is given to us as 276 in the problem. You have the standard deviation of the population, just the standard deviation symbol by itself. Okay, that is given as 81. What we need to find is the standard deviation of the sample. So to find the standard deviation of the sample, we are going to do the calculation that is given to us as the standard deviation of the population over the square root of the sample size. So that's going to be 81 over the square root of our sample size here, 40. Okay, so let's go ahead and find that. We can put that in our calculator as 81 divided by, and then we'll go second square root of 40 and close that parentheses. And we're going to get, and we'll do 3 decimal places when we're pulling these. So we'll do 12.807. Okay, so that standard deviation changes significantly. It changed from the population being 81 to now being 12.807. Okay, so it does change the calculation significantly when you're looking at a sample. Okay, but sometimes all you can do is get a sample. You can't get the data for the entire population. So now to do the problem, we have what is the probability that the mean of the sample will be less than 273. So you're finding that the probability of x being less than 273, you want to convert the x to the z-score, okay? Meaning you're going to use the calculation x bar minus the mean over the standard deviation of x bar. Okay, so that's x bar here is going to be the 273. Okay, that's given to you in here, the mean of the sample. Okay, so 273 minus the mean, 276, over the standard deviation of X bar, which we found up here, to be 12.807. Okay, so we'll do that calculation, which looks to be, let's see, 273 minus 276 is going to give us -3, and we're going to divide that by 12.807. So they're going to get a -0.234. Okay, now if we sketch this on our normal distribution curve, we have our mean is 0, okay, because we've now put this in terms of z, and -0.234 is pretty close to 0. I'd say it's probably roughly about right here. And the question we're asking is that the probability that it is less than this. So that means, what is this area to the left, because that would be less than, to the left of this value under this normal distribution curve that has a total area of 1. So what percentage of this curve is this? So we know just looking at that, that should be less than 50%, because 50% would be right here. So we want to get this value here. So we can look this up in our z table if we'd like. -0.234. And we can also put this in our calculator. So I don't have the z table up, so let's do the calculator first. So in my calculator, I'm going to choose normal CDF. And then since I'm going to the left towards -infinity, I'm going to choose -99 as my lower limit, my upper limit -0.234. And then my mean in a TI-84 would be 0, my standard deviation 1. So second vars, normal CDF, and then -99, and then for me, I'm using a comma, -0.234. So that's going to give me 0.407. Okay, so roughly 40%, 0.407. We want the probability, not the percentage, so we're going to leave it as a decimal. Let me pull up a z-score so we can also check on that table, or the z-table. All right, so -0.2 and then 3, so 0, 1, 2, 3. So we're pretty close, 0.409. That's definitely within the margin of error. It's 0.002 if I subtract the difference. So we're definitely within that margin of error where we did round when we found the standard deviation of X bar. So it made it slightly different, but either one would be accepted if you put that into the computer tool. Remember, the margin of error, I think, is 0.05. Okay, so let's just take a look now comparing Chapter 6 and Chapter 7. So how to know when we're going to use which calculation. Okay, so our example is credit card balances are known to be normally distributed, okay, with a mean of $2,870 and a standard deviation of $900. Okay, so they're telling us there's no sample that's given to us in here, so this is all credit card balances. So this is our population. 2,870 is our mean, and 900 is our standard deviation. A, what is the probability that any randomly selected credit card holder has a credit card balance less than 2,500? So again, we are not given the context of a sample. So you have to take a step back when you do the problem, okay, now and say, am I given a population or am I given a sample? And then from there, what calculation am I going to use? Okay, so here, any randomly selected credit card holder tells us population. Okay, so find the probability that X is less than 2,500. 2,500. So there we would convert 2,500 to a z-score using our normal z calculation, x minus the mean over the standard deviation. So that would give us, let's see, 2,500 minus 2,870 over 900. So 2,500 minus 2,870 divided by 900 gives us negative 0.411. So here's 0. And negative 0.411 probably about right here. And we want the probability that it is less than, so that is going to the left. So we're looking for this area under the curve here. So again, we can just use our calculator and go normal CDF. We're going to the left, so our lower limit is going to be negative 99. Our upper limit, negative 0.411. So second, VARS, normal CDF, negative 99, negative 0.411. And that's going to give us 0.3405, would round up to 1 there, so 0.341. Okay, so this area right here under the curve, that's about 34% of the curve that we're covering here, so 0.341. So part B is going to be where this slightly changes. So here you have, say you randomly select 35 of these credit card holders. Now we're looking at a sample. So not every question is going to have this here with sample in all caps. I'm just trying to show you just for the purpose of how these questions will look different. Okay, what is the probability that the mean credit card balance of the sample is less than 2,500? So a lot of times in the question it will say of the sample to clue you into that's the type of problem we're doing. So it's the same problem, okay, but now we're looking at a sample. So that means the denominator of our z calculation is going to be different. So in this case, you now have a sample size of 35. Your mean is still going to be the same, which was 2,870. And now you have the sample of, the standard deviation of your sample, which is the standard deviation of your population, which was 900, over the square root of your sample size, 35. So we'll find what that is. So 900 divided by the square root of 35 will give us 152.128. Okay, so now we work where we get the z value, but this time our denominator, instead of being 900, is going to be this 152.128. So we have 2,500 minus 2,870 now over 152.128. So 2,500 minus 2,870 divided by 152.128 gives us a negative 2.432. So then we graph this. Negative 2.432 is going to be way over here. So that's going to dramatically change our answer here. The percentage is going to be much smaller than what we had up here, 34%. But that's because we're only looking at a very small sample of 35 people. So it's got to be smaller, because then it would give you a more accurate or an accurate value based on those 35 people. So again, we'll do normal CDF. And then we're going to go negative 99, negative 2.432. Okay, so let's see, second distribution. So negative 99, negative 2.432, 0.008, if I round that up. Definitely a big change. Okay, why? Again, there's only 35 people in the sample as opposed to here, that's the population. That's all people who hold a credit card. So that might be something like 100 million, 200 million people. Okay, so of course, the number is going to be a higher percentage of them when you're looking at a larger amount of people. It's going to be a smaller percentage when you're only looking at a small sample. So really, if you wanted to kind of just take a key here, you have a smaller sample is going to have less accuracy. Accuracy. And then a larger sample is going to have a closer or a greater accuracy. And this is with regards to the entire population. So both of these with regards to the population. So it's always better to have a large sample size if you're trying to talk about an entire population. So think about something that you read in the news, right? Okay, let's say this was real in the news. They say, okay, well, they only do a sample of 35 people. They say, oh, less than 1% of people have a credit card balance less than $2,500. And you say, well, my credit card balance is less than that, so am I only in the less than 1%? Then you read through the article and you see, oh, they only surveyed 35 people. So yeah, that does seem about accurate. And who did they survey? Look at those pieces of information as you're reading through articles that give you, sometimes when you read the percentage, oh, this claim, that gives me a little bit of pause. Let me look through, see how many people are surveyed. What is that sample size? Okay, the greater the sample size, the more accurate of an entire population that's going to be. All right, so let's take a look at some problems from chapter 7. We've got about 10 problems here. So let's do the odds together. We'll go through the odds right now, then I'll let you do the evens on your own, and then we'll go over the evens. Sound good? Okay. So number 1, a population contains 14 members. The total number of samples of size 8 that you can select without replacement from this population is. So this is just kind of a throwback to chapter, what did we do this in? Chapter 4? Chapter 5? Binomial distribution is this a permutation or a combination? So just to remember what you're doing there. So remember, permutation is where the order matters. Combination is where the order doesn't matter. So this is where the order does not matter. So this would be a combination. So then this is just out of 14, choose 8. So 14, choose 8. And remember, do you guys remember where to find that in your calculator? Math, then probability, NCR. So 3003. So math, PRB, and CR. So actually we'll do 14, then we hit math, then we hit NCR, then we hit 8. All right, and then number 3, an error that occurs because of human mistakes. So that is just vocab back from 7.1. That's non-sampling error. Okay, we didn't make an error when we were sampling. That was a human mistake. I counted wrong. Okay, I wrote the number down wrong. Instead of you telling me that you were 32, I wrote down 23. Okay, that happens all the time. Let's see. Number 5, again, another vocab. The mean of sampling distribution of the sample mean is always equal to the population mean, always. Okay, so mean of a sample, that's mean of a sample, is always equal to just the mean of a population. All right, number 7, what is the formula for the standard deviation of the sampling distribution of the sample mean for a sample size of n drawn from a population with a mean, mu, and a standard deviation, So this is just the formula for the standard deviation of a sample. So that is the standard deviation of the population over the square root of the sample size. All right, and we'll do number 9, which is another problem. So we have a population, has a mean of 60.5, standard deviation of 13.5 in the population. Okay, this is just making our assumption that the sample size is large enough. That's what this is telling us here. The probability rounded to 4 decimal places that the sample mean, so now we're looking at a sample, of a sample size, 35 elements, selected from this population will be between 62.5 and 67.1 is what? All right, so a couple things we have to do here. So let's see what we have. We have a sample size of 35 given to us. We have a population mean of 60.5. We have a population standard deviation of 13.5. Okay, we want to find the probability that, let's see, we're not really given the context of this, so the probability, I don't know, maybe we'll say this is a test score is between 62.5 and 67.1. Okay, what is that probability given the population mean is 60.5? Okay, so we need to find the standard deviation of the sample of 35. So we'll do the standard deviation of x bar, which is going to be the standard deviation of the population given to us as 13.5 over the square root of our sample size of 35. So that's the first calculation we'll do. So 13.5 divided by the square root 35 is 2.282. Okay, now what we want to do is we want to convert both the 62.5 and the 67.1 to z-scores so that we can put them on a normal distribution curve. So I'll put a curve over here. And we'll convert those z-scores and then draw them on the curve. So for the first one, we will do the 62.5, so that's going to be a z. Change the color here. You will have the x bar, which will be 62.5, minus your mean, which is 60.5, over the standard deviation of the sample, and that's this 2.82 that we just found, 2.282. So that's going to give us, let's see, so 2 divided by 2.282, we're going to get 0.876. Okay, so if I have a 0 right here, 0.876, we're going to say maybe is like right here on this curve. Okay, now let's do 67.1. So we will go Z. The X will change to 67.1. Our mean is still 60.5, and we're still dividing by 2.282. So 67.1 minus 60.5 gives us 6.6 divided by 2.282. We get 2.892. Okay, so that's maybe right here. So we want to find this area in between these two numbers. So now we will just go normal CDF. Our lower limit will be this 0.876. Our upper limit, 2.892. So second bars, normal CDF, 0.876, 2.892. So we're going to get 0.188, and we want 4 decimal places, so 0.1886. Put it below so we can see it. Okay, so I always like to take these questions, if they don't give me a context, and put them to a context. So if I'm talking about test scores, maybe this was a really hard test. So the mean was 60.5, and in my class of 35 people, about 19% scored between a 62.5 and a 67.1. Okay, just to kind of help me with, all right, what does this even mean? Why am I doing these numbers? I always try to put them to some sort of context. All right, so I'm going to give you guys, let's see, I'll give you about 15 minutes to work on, 15 minutes to work on 2, 4, 6, 8, and 10, and then we'll go over them, and then we'll be out of here. All right, let's take a look at these. So go back to number 2. So sampling error is, you guys should have gotten B here, the difference between the value of the sample statistics and the value of the corresponding population parameter. That's vocab in 7.1. All right, number 4, the mean price of all magazines published in the United States is $3.65. Probably a little outdated. I think the cost has risen significantly since then. But the mean price of a random sample of 16 magazines is $4.30. The sampling error is, so sampling error is you're going to take the mean from the sample minus the mean of the population. So here you would do $4.30 minus $3.65, and that should give you 65 cents. Okay, so X bar minus the mean. All right, number 16, for a continuous random variable X, the population mean, sorry, number 6, I don't know why I said 16. Just add it, that's non-sampling error, human error there. I just added a 1 just because sometimes our minds do tricky things. All right, the population mean and the population standard deviation are 82 and 18, respectively. You take a simple random sample of 25 elements from this population. The mean of the sampling distribution of the sample mean is. So this is a classic question where they're throwing a lot of information at you, but you don't need very much of it at all. Remember that the mean of the population in a sampling distribution is equal to the mean of the sample. So it's just 82. So all of this stuff here, you don't need any of that. It's just noise. Okay, so you've got sampling distribution is equal to population mean. So it's just 82. All right, let's take a look at number 8. For continuous random variable x, the population mean and the population standard deviation are 95 and 40 respectively. So mean is 95, standard deviation is 40. Assuming the sample size is large enough, find the standard deviation of the sampling distribution for a sample size of, and then we have 3 different sample sizes here. So we're going to be using the formula for the standard deviation of x bar, which is going to be the standard deviation of the population over the square root of the sample size. Okay, so we don't need the 95, we need the 40. 40 is going to be the standard deviation of the population. That's going to be the numerator in all of these calculations. The denominator is what is changing, okay? So the first one, you are doing 40 divided by the square root of 49. Second one, you're doing 127. No, you're not. I'm sorry. You're doing 40 divided by the square root of 127. And then the third one, you're doing 40 divided by the square root of 450. Okay, so your numerator will be 40 in each of these. The denominator is what will change. So 40 divided by the square root of 49, which I believe is 7, is going to give you 5 and we'll do 3 decimal places, 714. And then for B, 40 divided by the square root of 127 is 3.549. And then 40 divided by the square root of 450, 1.886. Notice as the sample size gets larger, how this number gets smaller and it gets closer to that normal distribution, which is a mean of 0, standard deviation of 1. So the standard deviation gets closer and closer to 1 as that sample size gets larger. Okay, so the calculations, are pretty simple. It's just knowing which calculation to do when, which of course comes with practice. All right, let's take a look at number 10. So we have a population has a normal distribution with a mean of 51.4, standard deviation of 8.4. I'm just going to go ahead and write that down so I have what I need here. So mean is 51.4, standard deviation, population 8.4. All right, so assuming sample size is normal, probability, 4 decimal places, that the sample mean, so now we're looking at a sample, of a sample size 18, so our n here is 18, selected from this population, will be more than 51.15 is what? All right, so we want the probability that x bar is greater than 51.15, and I'm doing x bar instead of x because I'm doing a sample. So we will want to standardize the score by finding the z-score. So we'll do, the z-score is going to be x bar minus the mean over the standard deviation of x bar. So when I'm filling this out, I've got x bar of 51.15. I have a mean of 51.4. And then the standard deviation of x bar I do need to find. So let me go ahead and do that before I put it in my formula. You can put it in down here if you want. I like to do it separately, but that is a complete preference. So whatever you want to do there. So standard deviation of x bar here is going to be 8.4 over the square root of 18. Okay, so standard deviation of the population over the square root of the sample size. So 8.4 divided by the square root of 18. So I'm getting 1 point, it's probably going to be 980 there, or 97. Let's do 9799. Do that. 9799. All right, so my denominator is 1.9799. So I'll finish the z calculation. So let's see, 51.15 minus 51.4 divided by 1.979. So negative 0.126. Okay, then we'll draw our curve. And the probability is greater than, so we're going to go to the right here. So here's 0, negative 1.1 is very close to 0, probably closer than I drew it. And we're going to the right. So we're shading to the right, which means our lower limit will be negative 0.126, and our upper limit will be positive 99. So I'm going to go normal CDF, negative 0.126, positive 99, and then enter. So let's see, second vars, normal CDF, negative 0.126, comma, 99. So I'm getting 0.550, are we doing 4 decimal? Yeah, 5501. All right, and that's everything for 7.3, 7.4. Do you guys have any questions about any of these problems? Any questions? All right. So we will continue on Thursday with 7.5 and 7.6. We've got about 2 pages of new stuff to look at. And we are looking at now proportions in 7.5, 7.6. So that's when we're going to be given the context with percentages instead of the numbers. And then we'll have some practice problems. We've got a good bit of practice problems for that section. And then, is there a practice test at the back of your guys' packet?